Okay, let's begin. Hello and welcome everyone to the Thursday, October 29th press conference here at the virtual DPS meeting. This will be the final press conference of this meeting. I'm Shantanu Naidu, I'm the DPS press officer, and with us today is Rick Fienberg, who's the AAS press officer. He'll be helping us with Q&A and other technical issues that may come up. There'll be press releases for all the talks today, so watch out for those. If you missed yesterday's or any of the previous press conferences, or if you want to go back and look at them, they'll be available on the AAS press channel or on the meeting website if you click on press information and go to the second media advisory. Under the schedule, there'll be links for each of the presentations and press briefings. So some ground rules before we begin. All panelists, we'll be recording today's briefing and it'll be streaming to YouTube where it'll be archived for future viewing. All panelists will speak in order and then we'll go to the Q&A later. We've asked our panelists not to answer questions through the Q&A box. So please be patient for the Q&A session before they answer your questions. Okay, with that, I'll introduce today's speakers. First, we'll have Masahiko Arakawa from Kobe University, who will talk about resurfacing processes on asteroid Ryugu caused by an artificial impact of Hayabusa 2's small carry-on impactor. Next, we'll have David Dunham from KinetX Aerospace, who will talk about first occultation observations by a small NEO, Phaethon. Next, we'll have Matthew Clement from Carnegie Institute of Washington, who will talk about how Jupiter and Saturn's secular architecture constrain their early orbital evolution. And finally, we'll have Thomas Esposito from SETI Institute, who will talk about first results with a network of small digital and smart telescopes, citizen science for astronomy. And with that, I'll turn it over to the first speaker. You may start sharing your screen. May I please ask the other panelists to stop their videos and mute their mics.
Hi everyone, my name is Masahiko Arakawa, Kobe University, Japan. It's my pleasure to have a good opportunity to introduce our new finding here. So today I will talk about the resurfacing processes on asteroid Ryugu caused by an artificial impact of Hayabusa 2 small carrier impactor called SEI. This study was conducted by these Japanese Hayabusa 2 teams. So as you know, asteroid surface is covered with regulus layer. So impact cratering is the main mechanism of resurfacing on asteroid. So because impact can change the surface morphology and subsurface materials are ejected and deposited on the old surface. In addition, the surface vibration induced by the impact moves the boulders to erase the surface roughness. This is called seismic shaking. However, the intensity of the seismic shaking could be controlled by the internal structure. The vibration could be weak in homogeneous regulus layer and strong in regulus layer on base rock. So April 5th, 2019, Japanese spacecraft Hayabusa 2 succeeded to form an artificial impact crater on the surface of asteroid Ryugu. The crater was semicircular, and the crater growth toward the south was stopped by large block named Okamoto boulder. The crater had an elevated rims with a diameter of about 18 meters. Deployable camera 3 observed the eject curtain and the deposition, and DCAM 3 found a few boulders in the eject curtain. After the impact, Hayabusa 2 succeeded to collect the surface sample at 22 meters far from the crater center, called TD2 point. Therefore, this artificial impact was a good opportunity to study the resurfacing processes on asteroid by impacts. So we studied resurfacing process by using the pre- and post-impact images around the impact point. Next, I will talk about the result of the analysis using pre- and post-impact images. First of all, I will show you the digital elevation map of the SCI crater in the left figure. So, and the crater rim profile were studied using this map in these 6 areas. And there's some anisotropy of these profiles, but the average rim profile was approximated by the empirical equation in the middle figure. This equation shows the ejecta thickness at TD2 point is about 1 millimeter. However, this profile may fail to detect new boulders appeared after the impact. So the effects of boulders on the rim height were incorporated to improve the profile in the right figure. And the improved rim height is very consistent with the theoretical rim profile. According to this theory, the ejecta thickness at TD2 point is estimated to be 1.8 centimeter. Next, I will talk about the moved boulders. So we discovered 48 boulders moving from their initial positions. Here's an example of moved boulders. Here to here, you can see. This left figure shows the distribution of these moved boulders. This semicircle is a SCI crater. These boulders moves up to 10 meters. And we found several boulders excavated from the subsurface and deposited outside the crater. They are shown by green symbols here. We also noted that some of the boulders may be moved by seismic shaking, and they are shown by white symbols around here. The right figure shows the distribution of newly appeared boulders after the impact. Here is an example of appeared new boulders here and here and here. The 169 boulders with a size between 30 centimeter and 3 meter were discovered outside the SCI crater, as far as 40 meter. And finally, I will show you the disturbed area around the SCI crater. First of all, this left figure is a cross-correlation map, and it was calculated by comparing the pre-impact images with the post-impact images. If the surface was disturbed by the impact, the cross-correlation coefficient decreases depending on the degree of disturbance. So low cross-correlation coefficient area shown by this red and blue color mainly shows the ejecta deposit region. This middle figure shows the surface displacement map. Boulder near the SCI crater moved more than 10 centimeter up to 1 meter. And this disturbed area extends up to 15 meters. The small disturbed area also appeared further than 15 meters as patches and distributed randomly around here. According to these figures, we found more than 50% boulders in the area within 15 meters moved large distances enough to be detected. And about 10% boulders moved in the area between 50 meters and larger than 30 meters. So we can speculate that the homogeneous regulus layer at least as deep as 30 meters below the surface. And this is summary of my talk. So I'd like to emphasize that this finding on real asteroid resurfacing processes can be used as a benchmark for the numerical simulations of small bodies impact. So that's it. Thank you for your patience.
think I'm ready then.
David, we're not hearing you.
Oh,
Right, you are ready to go. You'll probably find it easier to use your arrow buttons to move your slides. To change slides, that is.
what's what happened? I don't know.
David, if your PowerPoint is frozen, perhaps you should close it and reopen it. And start, click play from the first slide.
Okay, let's see.
Uh, David, we can't hear you. Are you speaking? Oh, we're not able to hear your voice.
Can you hear my PowerPoint?
Oh, I can hear you now. Oh, we can't hear you. Is your audio in the PowerPoint? Uh,
Yeah, the audio narration isn't coming through. You'll have to speak your audio. I see what the problem is now. You thought that we were hearing your pre-recorded narration, but we're not. We only hear you speaking. You know, when you speak from your actual mouth.
It's not playing the audio.
You've got your headset plugged in, and that's where the audio comes from for the Zoom. So the only way that we would be able to hear something playing on your computer is if it's playing into your microphone, not into your ears.
Okay, maybe we should move to the next talk while we figure out or solve Dave's technical issue. So can Matthew do your presentation next?
Sure. Okay, good morning, and thank you for the invitation to come and talk to you all about our new research that is in press in Icarus right now. Our work has used over 6,000 numerical simulations of the early dynamical evolution of the solar system to refine our understanding of the primordial orbital configuration of Jupiter and Saturn prior to the so-called Nice model instability. The working title for this project has been the 2-to-1 resonance strikes back. So hopefully by the end of the talk, everyone's going to get that joke. We know from observations of protoplanetary disks, like the one pictured on the left, that the planets in our solar system grew within the circumstellar disk of gas and dust. Major motivating question for our research is in finding ways to reconcile the types and structures of planet systems that emerge from models of this planet formation process. Typically, these are compact collections of resonant orbits with the radially diffuse system of planets that exists today. More on that later. This process is a bit like trying to figure out what caused a car crash by only looking at its aftermath. How fast were the cars going, in what directions, who was at fault, and were there other vehicles involved that ended up driving off without leaving behind their insurance information? Because we don't know the initial conditions, there are perhaps an infinite number of possible paths that the various cars might have followed before and during the crash. Thus, we must study the entire event statistically in an attempt to ascertain what actually transpired. In the same manner, when studying the assembly of orbits in the solar system, we have to turn to large batches of numerical simulations to robustly investigate each different plausible primordial configuration that is produced in hydrodynamical models of planet growth within the primordial nebular gas. Through this process, previous studies in the mold of our own generate giant lookup tables of the various probabilities each set of initial conditions for the planets has for replicating different aspects of the modern solar system, like those from Niswornia Morbidelli 2012 that are shown on the right. The car crash analogy is actually quite relevant in the solar system, as we are fairly confident that the giant planets attained their modern orbits through an epoch of violent instability after forming in a more compact configuration. Often referred to as the Nice model, interactions with remnant planetesimals, like those plotted in green, like Pluto, in the primordial Kuiper belt perturb the infant giants out of their compressed, quiescent chains of orbits. When this happens, the entire solar system experiences a global instability. While it is impossible for us to back calculate the precise evolution of the solar system during this violent and chaotic episode, it is important that we're using the correct models and correct initial configurations when studying this violent formative epoch of the solar system. As the young Earth was an innocent bystander during this multi-car pileup of 18-wheeler trucks in the outer solar system like Jupiter and Saturn, it is thought this event sculpted many aspects of the Earth's formation, including its modern volatile composition, its atmospheric evolution, to name a few. So what are the correct initial conditions for the instability? As Jupiter and Saturn are the most massive planets, their mutual configuration is of utmost importance in driving the subsequent dynamical evolution of the system. Early models indicated rather convincingly that the interactions with the nebular gas would have forced the two gas giants into a 3-to-2 mutual resonance, where Jupiter completes exactly 3 orbits for every 2 of Saturn's, and the planets repeatedly aligned every 3 Jovian cycles, as indicated by them turning red in this video. If you watch one more cycle of Jupiter, here they'll align and turn red. A major motivation for research was the systematic difficulty of generating the modern Jupiter-Saturn configuration when evolving this 3-to-2 resonance through the Nice model instability. In particular, these instabilities are quite violent, and Saturn is typically kicked out into the distant solar system if it experiences a strong gravitational encounter with Jupiter. This top plot here shows Jupiter's final eccentricity versus final distance from Saturn. You can see that the solar system, represented by the red star, lies at the extreme of the distribution of possible outcomes when the gas giants start in the 3-to-2 resonance. Additionally, Saturn's orbit typically finishes overly eccentric or non-circular relative to Jupiter's, and also perturbs Jupiter more strongly than in the modern solar system, as is depicted in the bottom panel, again with the solar system red star falling at the extreme of the range of possibilities. However, modern hydrodynamical models have shown that for certain gas disk conditions, Jupiter and Saturn are more likely to be captured in the more distant 2-to-1 resonance. Additionally, as the planets carve out larger mutual gaps while forming in the gas, they also attain higher eccentricities, or more non-circular orbits as they grow. Thus, their eccentricities can already be similar to the modern values prior to the instability. Through our dynamical analysis, we found that for a variety of different possible 2-to-1 configurations, such as the 8 depicted here, the solar system result depicted with the red star represents a more typical outcome, particularly in terms of the relationship between Jupiter's eccentricity on the y-axis and its offset from Saturn on the x-axis. In conclusion, our work finds that Jupiter and Saturn were likely born in this 2-to-1 resonance. Our most successful initial planet chains contained either 1 or 2 additional planets in between Saturn and Uranus that are ejected during the instability. And no, they didn't leave their insurance information for us to track them down later. These extra planets were initially locked in 4-to-3 resonances, and the infant Uranus and Neptune were captured in mutual 3-to-2 resonances. More importantly, we now have a set of successful instability simulations that we can use to study the evolution of other parts of the solar system. While we find that the primordial 3-to-2 Jupiter-Saturn resonance is still viable, albeit with lower statistical likelihood, our 2-to-1 configurations do not suffer from the same systematic problems, and thus the 2-to-1 resonance strikes back. Thank you for your time.
Okay, we'll have Thomas Esposito go next.
Okay. All right, good morning. My name is Thomas Vizito. I'm a research assistant at both the SETI Institute and UC Berkeley. I think it's pretty fair to say that this has been a stressful year for most people. So I'm pleased to share with you today what I find to be a feel-good story of a growing network of citizen astronomers contributing to real science from their backyards. In these cases that I'll talk about today, teaching us more about the shapes of asteroids. And I'm presenting on behalf of those citizen astronomers and my colleagues at SETI, the telescope maker Unistellar, and Charles University in Prague. The citizen astronomers that we're working with are using enhanced vision telescopes, or EV scopes for short, designed and sold by Unistellar. These are consumer telescopes, accessible, easy to use. You can order one right now if you want. But they're also powerful tools for science and education. And the science side is where we at the SETI Institute come in. The SETI astronomers are partnering with Unistellar to select and design science campaigns and put out calls for observations from the Unistellar citizen astronomers. When one of them observes, the images are recorded by the camera built into the EV scope and later wirelessly uploaded directly to the cloud. Then we take those data, process them, analyze them, and send the results back to the observer, log them in the appropriate astronomy databases, publish them, and so on. This network of astronomers, which we only formed this year, it's already large and it's growing daily. There are about 3,000 EV scopes around the world now, and there will be over 4,000 by December in an even wider array of locations. All right, so there are tons of asteroids, both near and far from Earth, and they can tell us a lot about the origin and evolution of our solar system. That's why people are doing these daring missions like Hayabusa 2 and the OSIRIS-REx return mission recently with asteroid Bennu. And of course, in some cases, those asteroids may pose, maybe, a threat to us here on Earth. So it behooves us to learn as much as we can about where they are and where they're going. And on those notes, here's one of our recent results that shows the scientific promise of this EV scope network. It comes from observations of the main belt asteroid 787 Moskva, which was selected by SETI researcher Joe Asensio, then observed by 7 different citizen astronomers across 4 countries and across several days back in August. Now, from those EV scope images, Joe measured the asteroid's flux, in other words, the amount of sunlight reflected by its surface over time. And that's shown in these light curves in the top left. From the 7 EV scope light curves that he measured, the flux variations over time confirmed the asteroid's spin period of about 6 hours. We also submitted these light curves to the IAU's Minor Planet Center database for broader analyses in other work. Then by combining these new observations with previous ones, a team at Charles University found a new shape model of the asteroid, shown to be the elongated shape in the bottom left animation. And tying that shape in with mid-infrared measurements to confirm the asteroid's diameter, tying that shape in with mid-infrared measurements then confirmed the asteroid's diameter to be 25 to 30 kilometers. So the EV scope observations taken by the citizen astronomers directly connected to the measuring the size, shape, and spin of this asteroid. And as a fun little touch, I think, Unistellar and SETI together 3D printed a tiny version of the asteroid to send back to the participating citizen astronomers as a thank you and also as a reminder of their accomplishment. I mean, I've been doing astronomy for 10 years and no one's given me a 3D printed anything for my work, so I'm pretty jealous about that. This was one of the proofs of concept for our planetary defense program to help nail down asteroid orbits, sizes, and other properties, and particularly for these near-Earth asteroids. And our goal is to regularly offer this type of campaign with calls like the one shown on the right here for Moskva in August. And another type of asteroid observation we're doing is occultations. This is when an asteroid in the solar system passes between us and a distant star, temporarily blocking that star's light for a narrow strip of shadow on the Earth. And the timing of the occultation and how much the star's light dips tells us about the orbit of the asteroid and its shape, including potentially if it has its own miniature moon or ring system. And because the path of the occultation shadow on Earth is usually narrow, the mobility of the EV scope, which fits entirely in a backpack, you can see 3 of us carrying them here on the right. It's a real advantage to quickly packing up the telescope, driving a few minutes or a few hours to a good site to see the occultation, and then going on sky just a few minutes after you get there. Now, one of these occultations was by the main belt asteroid 943 Begonia, just last month on September 24th. The campaign was initiated by the Unistellar engineer Ines de Muis, who leads the occultation campaigns. In this case, among several EV scope observers, 2 of them detected the occultation. On the right, you can see an example of the positive report that goes back to the observer, including the light curve on the bottom that shows the star's big flux dip. Now, detecting the occultation once tells us about the asteroid's position in orbit, but having 2 detections, and importantly from 2 different locations, one in Arizona and one in New York, tells us about the asteroid's size and shape. And in this case, Ines's measurements showed Begonia was more round than expected, and it could be up to 20% larger than previously known at 83 kilometers in diameter. Now, since starting in February 2020, we've run 53 occultation campaigns, including about 100 different observers and 10 positive detections. And at the moment, we're running about 6 occultation campaigns per week per continent, with positive and negative detection reports getting submitted to the Euraster and IOTA databases. And just briefly on the education side, SETI and the University of Southern Queensland in Australia are working with others to develop a plan with K through 12 schools, junior and community colleges, and also some 4-year colleges to get EV scopes into the hands of their students and teachers. One case study for such inquiry and project-based collaboration was led by Professor Todd Duncan of the University of the Pacific, who rather than having his students learn about parallax from a book or a video, he had students collaborate with the EV scope observers on opposite sides of the US, combining their images and measuring the parallax of a near-Earth asteroid. So you see here on the right, there are 2 different images stacked over time, one from Virginia and one from Oregon. And so just to wrap up, that was just a brief glimpse into some of the science that we're doing with this new network of thousands of backyard telescopes. These asteroid studies are really just the tip of the iceberg. We've now validated the use of EV scopes for accurate photometric studies. So we can expand into other areas, such as transiting exoplanets, which is my specialty, variable stars, supernovae, and other transient events, which substantially broadens the ways that we can bring observational astronomy to classrooms and to homes. So we hope you'll stay tuned. Thank you.
Okay, we'll go to Dave next and try again.
Okay.
We still can't hear the narration, so if
Oh,
you can read it out, maybe that would be better.
okay. Okay, let me start it again then. You can hear me all right now?
Yeah, we can hear you.
Okay. Um, oh, wait. I have to. Trouble is the audio from the presentation, I have to mute it and don't see how to do that.
You can just turn off your speaker, and that way you won't hear the audio.
Right. Okay. Let's see. Yeah, I'll just unplug this. Can you, wait, no, you can't hear me that way, but if I can, yeah, let's see. Okay, can you hear me talk now?
Yep.
Okay, no, let's, okay, can you hear me?
Yes. Can you hear us?
Yes.
Yeah.
Let me see if I can. Okay. Let's see. Gosh. So what I think I'm doing is just going to show the slides this way. So anyway, let me try to get through this quickly. Phaethon is the parent body of the Geminids meteors. You can get a better narration of all this if you download my PowerPoint from the website given in the press release. So
you need to share you need to share your slides though, David, because we don't see anything except video here.
Okay, yeah. I've here. Okay. Now, can you see these? Can you see the slide and hear me?
Yes.
Okay. Okay, good. So I'll just do this. Phaethon has this very unusual elongated orbit passing so close to the sun that it receives more intense sunlight, almost 300 times that of what it receives at aphelion. So it receives this thermal shock each time it goes around the sun every approximately 1.5 years. So this is causing the meteor stream to come off of it. The Japanese Space Agency plans to send their Destiny Plus spacecraft by Phaethon in 2025, so they're especially interested in learning more about it. And radar observations show it's about 4 miles across. This shows the geometry of an asteroid occultation. Tom already showed a little bit about this, but this just shows as the asteroid casts a shadow of a star on the Earth's surface, and several observers set up telescopes across the predicted path. And then if they time the occultation as the shadow sweeps over them, they can build up this observer's view of the asteroid. This bright star visible with binoculars was predicted to be occulted by Phaethon in July 29th, 2019. The JAXA people requested that we try to observe this event. This was by far the smallest object that anyone had ever tried to predict and observe. So we ended up setting up this network of 66 stations. We actually had a few more that we planned in the end. With the tightest spacing ever set up for any occultation, with the stations only 680 meters apart. about the height of the Empire State Building. This was also one of the larger professional amateur collaborations for an occultation by an asteroid. The inset shows the line for one of the observers, A31, Richard Nolthenius. And this shows his setup on the right and shows the, I'll play his video. I think I can do that. Come on. Okay. Let's see, it didn't show. Let's see if I can get from the beginning. So you look at the star in the center. There, disappeared. And below shows his light curve. Showing the disappearance and reappearance, similar to what was shown by Tom. But anyway, this shows the panel on the left shows all of the observer lines plotted in the sky plane. Most of the observers had no occultation, but the inset blow up on the right shows the 6 observers, including Nolthenius, who did have an occultation. And after that occultation, another one was observed 2 months later, which allowed us to refine the orbit and the predictions for 4 more occultations, which happened during October 2019. And then we even got an occultation early this month. Each occultation allowed a better improvement of the orbit as time went on. So Phaethon's orbit is pushed slightly as it sheds mass during each solar pass. The non-gravitational force is much smaller than the case for comets, but the occultations are far more accurate than regular astrometric observations by a factor of about 100 to 1. So they provide strong constraints on an object's trajectory. The observations of Phaethon were good enough that they allowed a 3-fold improvement in the determination of the small non-gravitational force causing by the mass shedding. The information helps shed constrained physical models of Phaethon's mass loss and results and allowing long propagations of its trajectory. The techniques demonstrated by these campaigns can be applied to other NEOs, including potentially hazardous ones, to characterize them and greatly improve their orbits, contributing to an improved assessment of their risk. The pro-am collaborations of future occultation campaigns can inspire and educate future generations of astronomers, as well as help determine the physical and dynamical properties of small bodies throughout the solar system. Sky observers everywhere are invited to participate with IOTA and the Southwest Research Institute in this exciting work. Opportunities are frequent. In recap, Phaethon is a strange active asteroid producing the annual Geminids meteors. The July 2019 occultation provided a rare opportunity to learn more about Phaethon and its orbit and JAXA requested observations. And one of the larger pro-am collaborations, 7 SWIRI telescopes and 45 from IOTA recorded the star in the tightest ever occultation fence, netting 6 chords that showed the size and shape of Phaethon. The observations and refinement of the orbit resulted in the successful observation of 6 more events. The occultation data improves knowledge of Phaethon's mass 3-fold, enabling more accurate predictions of its future path. Occultations can become an important technique in improving our asteroid catalog and help secure the knowledge of future motion of near-Earth objects, some potentially hazardous for long time periods. The efforts demonstrates how exciting occultation campaigns can give interesting new information about small solar system bodies, even NEOs. Others are encouraged to take up this activity and get my science presentation, the longer one, at the link given. So thanks for your attention.
All right. Thank you to all the presenters for their wonderful presentations. So can all the panelists turn on their videos, but keep their microphones muted for the Q&A? So if anyone has a question, please type it into the Q&A box at the bottom of your Zoom. So far, we don't have any questions, right? Right.
I don't see anything in the box at the moment. I actually have a question for Masahiko Arakawa. When you showed the before and after images of some of the boulders that moved, it almost looked like the boulders that shifted maintained their relative positions to each other. You know, like there was a clump of 4 boulders that moved, and the pattern of those 4 boulders after the impact was very close to what it was before. And I'm wondering if there's an explanation for that, or if I just wasn't seeing it right.
Yes, thank you for the question. It's very difficult to answer right now. So some of boulders, so it looks like that. It may be the boulders move together by seismic shaking. So almost receive the same acceleration by the seismic shaking. And that means the boulders moved almost the same distance from the initial position, I think.
Okay, thanks.
I had a question for Dave and I guess also Thomas. Is there another NEO you're planning on observing or for occultations?
Yes, we're going to be looking into those, especially Sisyphus and Tantalus are good opportunities, objects similar in size to Phaethon that we should be able to do. And also they're of some importance because they are potentially hazardous objects, and they don't have any radar opportunities for many years to come. So occultations can give some accurate data points between the less frequent ones we get from radar. I should mention, incidentally for Tom, that one of the telescopes in our chain of observers was an EV scope that Frank Marchus took down to get into the path. He was in one of the lines, though, that didn't have an occultation, but he did contribute.
Oh, that's awesome. I wasn't aware of that. So yeah, Frank actually leads the science group at SETI for our Unistellar collaboration. And yeah, just in terms of our own campaigns, you know, I can't name a specific NEA or NEO that we're pointing towards next, but we do have you know, several occultations per week that we alert our observers to, and then, you know, kind of as they come up. And then in terms of the planetary defense, you know, we do plan to have a few of those kind of monthly campaigns. And again, that's kind of as Joey and Ines see new targets, that's when we alert the network.
Yeah, your EV scope network will be great for expanding what IOTA has been doing over the years. So allowing a lot more people to get into the game. So we appreciate that.
Yeah, we're excited to help with it.
Well, I don't see any more questions, Shantanu. So if you'd like, we can wrap up. Our hour's almost up anyway.
Okay. All right. In that case, thank you everyone for this wonderful week of presentations, and thanks to all the audience and the wonderful questions we've received so far. There won't be a press conference tomorrow, So this will be it for this DPS. And I hope to see all of you next DPS for more exciting discoveries and presentations. All right. Thank you, everyone.
Thank you.